Hello everyone, my name is Guanyan Yang. Today I will present our research on enhancing code security testing using deep learning techniques, specifically focusing on Python programming language. And our goal is to improve the efficiency and effectiveness of security analysis in the software development process. First is introduction. We know that security testing is crucial in software development to prevent exploitable vulnerabilities within applications. And traditional methods often rely on manual inspection or rule-based approaches, which can be time-consuming and prone to human error. With advancements in natural language processing, we can explore new avenues for improving this process. Also, deep learning offers significant advantages for security testing by automating complex pattern recognition tasks. An LSTM model is a type of recurrent neural network and is particularly effective in handling sequential data, making them suitable for analyzing code structures. So, in our methodology, we use such techniques to detect vulnerable code. In our methodology, we start with dataset preparation, followed by exploring two embedding methods to generate code vector representations. We then train our LSTM model to analyze the code for potential vulnerabilities. And then we will introduce the related work of our study. Firstly, the applications of machine learning in vulnerability detection is highlighted. The dataset used by the authors come from Debian, GitHub, and synthetic samples from the set Ivy Juliet test suite, with all samples written in C language. And 3 open source static analysis tools were used for leveling. They employed a convolutional neural network and the recurrent neural network for feature extraction, followed by using the random forest algorithm to learn the feature and classify vulnerabilities. On the set IB dataset, the model achieved an F1 score of 0.84, performing well. Yeah. However, when applied to the Debian and the GitHub dataset, the F1 score was feel terrible. Yeah. Indicating that the model performs well on synthetic dataset, but not as effectively on real-world dataset. Next year, another method was being proposed. The authors follow the suggestion to directly mine datasets from GitHub and use word2vector as the embedding method, employing an LSTM model to learn vulnerability features. Similar to our research, the model achieved good results in detecting code weakness. However, there are still some aspects worth exploring. First, in terms of embedding methods, we believe that Codebird has better potential compared to word2vector. We assume that. And second, the hyperparameter of the model are crucial for training, and their study only briefly discussed parameter tuning. We believe that more in-depth research on parameter tuning can achieve better performance. Overall, the research also provides guidance for our research direction. And later on, we will using the result as comparison to our model performance evaluation. I want to introduce some existing static testing tools, and the first is Bandit. It is recommended by OWASP as a tool for scanning Python source code weakness. It was developed by the security team of OpenStack and is now maintained by the Python Code Quality Authority. This project still has people until recently contributing to. It is a project with a very active community. And the testing used by Bandit is carried out in a robust manner. That is, various patterns are defined in advance, which I can plug in the tool. Through this defined test plugins with scanning the source code, if an artifact first, if a good pattern matches, it will be classified as having a vulnerability. The following figure is the scanning process of this tool. First, Bandit will convert the source code into the format of abstract syntax tree, and then parse it. During the parsing process, it will compare it with the test plugin defined first. And finally, it will generate a complete test report will be issued. If there is a vulnerability, it will also indicate in detail which part of the program it is considered to be. And the second one is checkmarks. Checkmarks is a commercial static security testing tool. That is widely used in code security testing. It can be automatically analyze source code to find potential security vulnerabilities, helping developers find and fix security issues at an early stage. And checkmarks is support multiple languages and frameworks, including Python, Java, C#, JavaScript, and so on. So it has a wide range of applications. Now I want to talk about our methodology. First, we'll overview our approach, and this figure illustrates an overview. We collect the vulnerability dataset from GitHub and utilize Codebird as an embedding method. After transferring the source code into a vector representation, we train a STM model to extract the vulnerable pattern from the code. For data collection and labeling, we choose SQL injection vulnerabilities as our detecting objective, since it is reported as one of the most common vulnerabilities by OWASP and CVE databases. On top of that, it has syntactic features that can be learned by a deep learning model. To collect the SQL injection dataset from GitHub, we employ the PyDriller tool to assess us. Applying keyword to filter the commit we want. For example, the commit message contains SQL injection fix or SQL injection prevent. When we consider the change part as it potentially would cause SQL injection. Therefore, we might the commit and mark as the change part as vulnerable. And next is the data labeling part. We first analyze the commit message content, such as SQL injection prevention or fixed SQL injection vulnerability, which suggests that the code change may contain vulnerabilities that have been addressed. Then we obtain the code before the change and label the modified parts as vulnerable, while the unchanged parts are labeled as clean. The adjacent figure shows a simple commit from our SQL injection vulnerability dataset. We label the red part as vulnerable, while the green part, which shows the code after the change, is not labeled as clean. This is because the code after the change is excluded from the dataset, as it is possible that the vulnerability hasn't been completely resolved. In the figure, the part after the change still has concerns about SQL injection. After dataset is prepared, next thing we do is sending this data to an embedding layer to generate the vector representation of source code. And we leverage Cobra as an embedding method for multiple reasons. First, Cobra is pre-trained on a large corpus of both natural language and programming language data. Less extensive pre-training helps you learn a rich representation of code in natural language, making it effective in understanding and embedding code. And Cobra is built on the transformer architecture, which was proven highly effective in capturing long-range dependencies and contextual information. And this architecture allowed it to generate high-quality embedding that capture the semantic meaning of code. And it has demonstrated strong performance on variables, benchmark, and competition related to code understanding and generation. And another is this feature make Cobra a powerful tool for generating high-quality embedding for code. After preprocessing the data, we can start training our LSTM model. And to implement the LSTM model, we use the Keras library. There are three layers in the LSTM architectures: LSTM layer, Java layer, and depth layer. And to yield a better performance, the hyperparameter setting of the model must be carefully considered. And this table shows the hyperparameter of the LSTM model. Due to space constraints, we will not discuss the detail of parameter settings. And below shows the result of the model performance on detecting SQL injection within source code. One thing that has to be mentioned is that the accuracy here is reported only for completeness reasons. Due to the data imbalance, we can expect that most of the code will be clean, and vulnerable parts are relatively rare. Meaning there are many more negative parts than positive parts. We can see that our model yields a good result on vulnerability detection. And next, talk about drawing from the research conducted by these authors who trained a word-to-vector model for Python source code embedding, followed by an LSTM model to learn vulnerable code patterns. We aim to utilize the finding as our baseline model and compare its performance within our own. To do this, we reproduce a model and train it on the same data set. Our results shown in this table. It demonstrates that our model performs better, likely due to Cobra's self-attention mechanism, which enables better retrieval of contextual information compared to word-to-vector. And additionally, Cobra's simultaneous training with natural language proof advantages. As modern software development often emphasize writing human-readable source code with meaningful names for functions and variables and detailed code documentation. This allows semantic information to be extracted from the source code using techniques intended for NLP. To further analyze our model in real-world case, we collected another SQL injection vulnerability dataset and tested it with some SAST tools, and Bandy and such as Bandy and checkmarks. And this table shows the testing results on 97 Python files that might contain SQL injection vulnerability. And the precision of Bandit is 1 due to the predefined features. It has very little chance to generate false positives. We can see that our model performs better. It is likely because the SAST tool often relies on pre-trained features by humans. This feature might not be able to cover all vulnerable patterns, since there exists tremendous forms of vulnerability. And so, deep learning, on the other hand, learning from large amounts of data, can capture the semantic meaning and predict the vulnerability. Let's look at an example. This is one of our samples for SQL injection. On the left, we have our model prediction result, and on the right, we have the bandit scan result. We can see that both sides mark the same sections, and both detected code that might be at risk of SQL injection. In this sample, when performing the query, the email variable is directly embedded. This means that if an attacker inputs a SQL command in the email field, unexpected things could happen. One of the correct approaches is to parameterize the email variable and pass it as a parameter. Using Python as an example, you can convert it into a table data type to prevent SQL injection attacks. And finally is conclusion. In this research, we designed a model for Python SQL injection vulnerability detection by reproducing previous work. We found that the codebase is more suitable than word-to-vector for source code embedding tasks. After that, we compare our model with two SAST tools in real-world cases, and the result shows that the deep learning model has the potential to win against a traditional static analysis tool on vulnerability detection. In addition, our model architecture can further expand to other vulnerabilities and even other languages. Also, we are conducting more experiments to ensure that our method can detect our different types of vulnerabilities. This is all of my presentation. Thank you.